increasingly the role of the human inventor is not going to be to design the physical structure of products. You can do that if you want to keep doing it, but you won't need to in order to be an inventor. You won't even need to know how to. Instead, the role of human inventors will increasingly be to define the problem to be solved, to know how to define the problem to be solved in a language that a computer can understand, and perhaps also to provide input in the form of judgments, aesthetic, other kinds of subjective judgments to a computer. And the role of the computer will be to synthesize, analyze that information, also to generate, evaluate, and modify potential solutions and provide that back to humans. So another thing that human inventors will need to do is learn how to work collaboratively with computers and adapt their own skills to include those that are not yet automated by computers. Some results of this shift upward I found from interviewing people for the book are that when you use a computer to design the physical structure of a machine or other device for you, often the results are very surprising. The NASA antenna is a case in point, and that's why I showed it. It has a bizarre shape that admittedly no human antenna engineer would have thought of using. With John Coze's controller, he documents in Genetic Programming 4 coming up with controllers that had characteristics that human controller designers thought were impossible to achieve. And so it turns out that some of the best features of a human engineer, namely that intuition that places like MIT try to get you to develop as an engineer, often can have a flip side, which is they can hold you back. An intuition can also turn into a bias or a blind spot. Software doesn't have blind spots. It won't stop itself from considering possibilities that contradict conventional design wisdom, conventional thinking about what makes one design better than another. A similar related consequence, and whether you see it as a positive or a negative, I'll leave to you, is that often the results are not even understandable to human experts. Sometimes a product produced by one of these processes works. You can demonstrate by experiment, by simulation or real physical experiment, that it does work. But you may not be able to figure out why. And depending on the application, it may not matter why. But again, with the companies I spoke to, they've told me that sometimes they can't use those kinds of solutions. You can imagine if you designed a breathing tube for use by astronauts in a space station, and your test showed that it worked, but you didn't know why. You probably wouldn't want to use it because you also couldn't understand whether it might fail under some unusual circumstance. Whereas if you designed it from some well-understood principles, you couldn't be guaranteed, but you'd have a much higher likelihood, you'd have much better confidence that it wouldn't fail under circumstances that you had not explicitly verified. And as I said earlier, this technology, even though in some ways can replace certain kinds of skills that human inventors traditionally have had, namely physical design, testing, experimentation, those who know and who learn how to leverage it can actually use it to become better and more effective inventors. And I spoke to Greg Hornby, who was one of the people on the NASA team. He said that's really how he uses the technology and tries to encourage people who work for him to think about it. It's like a brain booster. It's a way of augmenting and increasing your skill. He says he views a bachelor's degree engineer with this technology to have the kind of the effective inventive skill of someone with a PhD.